Right. And welcome, everyone. Welcome to the Brown Bag. Before we start, do we have any announcements? Any announcements today? All right. I will introduce our guest today. He's a known member of the community. He currently works at Mile 2 as Cognitive Systems Engineering course, John Flach. He's also an emeritus professor at Wright State University in the psychology department, where we are now. He studied for his PhD at Ohio State University with Rich Jagosinski. His long career included research on human performance, control of locomotion, design of graphical interfaces, human decision-making, resiliency in organizations. He wrote a few books, among which Control Theory for Humans, Display and Interface Design, and last one, What Matters, a Meaning Processing Approach to Cognition. And I guess I could say more, but I'm going to stop here. Welcome, John. When you're ready, the floor is yours.
Thanks, Jan, and thanks for the invitation to present this brown bag. We do a lot of our work on Google Hangouts and stuff, but I have to tell you, it's really strange giving a talk to my computer instead of a live audience. So I actually was probably more nervous about this talk than most talks I've given. So I don't know where you guys were in 1978, but probably many of you weren't even a twinkle in your mother's eye at that point. But June 1978, Rich Jagosinski sat me down in front of an analog computer and linked together two integrators in a circuit and showed me that it created a sine wave. And that and what I learned from Rich as a graduate student about control systems and dynamics has shaped everything that I've done ever since in my career and how I look at human performance. And so what I'd like to do is talk to you about this idea of circles and the implications for how we think about how we do research on human performance and how we support human performance in design. So the idea of a closed loop circuit and the implications for the social sciences was really introduced in a series of meetings referred to as the Macy Conferences. And the originator of this idea was Herbert Wiener, who you see here. And you might recognize some other big names in terms of like John von Neumann, Heinz Forster. Ralph Gerard was a neuroscientist. Lawrence Frank is listed as a social scientist. Heinrich Clover and Molly Hauer were both listed as psychologists. And this is another picture from one of those conferences, but there are some other names that people might recognize: Gregory Bateson, Claude Shannon, information theory, Walter Pitts and McCulloch, Warren McCulloch's also there, Heinz von Forster, and Margaret Mead. And these conferences were all looking at this idea of cybernetic and control systems and the implications. And once Wiener introduced this idea, Walter McCulloch was really one of the big advocates, and he said, we see this all over the place. We see these circuits all over the brain. And similarly, someone like Margaret Mead says, yeah, we see these circular systems in cultures and societies, and these circles are everywhere. And so what I like to do is explore some of the impact. And one of the fundamental premises that has shaped my career, and this actually, I first learned about this in a book by Bateson, But this is a sea squirt. And the sea squirt starts the first part of its life as a free-moving animal, and it has a primitive eye and a tail and a nervous system, and it moves around and locomotes through the environment. But then in the second phase of its life, it attaches itself to a surface. And once it attaches itself to its surface, it digests its brain. It eats its own brain. And the point is that the brain is really important when you're moving around in the world. But once you locomote, once you attach yourself to a surface, in a sense, become a plant, the nervous system is a very expensive thing to support. And so you don't need it anymore. And the kind of the premise is this quote from Rodolfo Linus: the generation of movement and the generation of mindness are deeply related. They are, in fact, different thoughts of the same process. In my view, from its evolutionary inception, mindness is internalization of movement. And yeah, that is the fundamental premise that's shaped almost everything I've done as a scientist. So the talk, there's three kind of things that, I want to do a kind of a quick little demo of the weirdness of circuits. And weird, not for anybody who's had any exposure to control theory and probably not to most engineers, but it was weird to me as a young psychologist learning about psychology. And I think it is also weird in terms of the context of a lot of our research. And I want to give a little sense of that. And then what I want to do is explore 4 different ways to look at the basic coupling of perception and action in a circle, and how that's influenced how we study human performance. And then I'd like to close with trying to kind of bring those 4 perspectives together in kind of a both-and integration in terms of multiple interacting loops in a circuit. So let me start with this. So these are 2 simple elements, control elements in many control systems. So again, the transfer function, you put a step, and one way that to kind of interrogate these systems to understand the internal dynamics is to put a step function into the system. And so you put a step into the system, and if the system's a simple gain, you get a step out the other side, but the size of the step is magnified or minimized depending upon the gain. So if this were a gain of 0.5, the size of the step would be half the size of the input. If it's 2, it would be twice the size of the input. The other element is an integrator. And if you put a step input into an integrator, what you're going to get out is a slope. So the integrator is just summing that input over time. So it's adding it up, it's accumulating. You can think about it as an accumulator. And if you put these things both together in a series, it doesn't impact the shape of the outputs of these things. You get the same outputs, and it's kind of a linear. So, you put in a step of a certain height, gets magnified by twice, and then the integration, the slope of the integration increases. So the data accumulates in the integrator at a faster rate. Okay, and so you can predict the combinations by knowing the transfer function to the elements. But what happens when you put those 2 things together in a circuit? And when you put them in a circuit, you get emergent properties that are very difficult. They're difficult to interpret from the transfer function to the elements. And in fact, you can get a variety of outputs. And this variety is a function of 2 primary things: the gain of the system and the time delays that it takes for the signals to go through those loops. And if the gain if it's stable, a relatively low gain, you're going to get more or less a step out. You put a step in, you're going to get a step out, an approximate of a step out. But as the gain increases, you might get a little overshoot first. At a certain gain, you're going to get oscillations. You're going to get a kind of a sine wave out. And at a still higher gain, those oscillations are going to magnify over time and the system becomes unstable. So this property of stability is not a property of the elements, but it's a property of the circuit. And it's actually difficult, at least for me, to intuit that property of the circle from knowledge about the component elements. So the fact that if I look at the input of the gain and the input of the integrator, or even the combination of those in series, it's really hard for me to imagine that this is the kind of output you get from the circuit. It's even a little bit more interesting when we look at the components, because those properties of that circuit, those are constraints on stability. And so those constraints have to be, the stability constraints are properties of the linking that the elements have to satisfy. The step input, an analog of the step input is Fitts law experiment. So in the context of Fitts law, the initial position of the step is your home position, and then the target comes on, and that's like a step input to move to another position. So it's an immediate sign to move to another position. And you put the human in that, and what you're going to get is approximately a step out if the system that he's controlling is a gain. But if the system, the element is an integrator, so it's a velocity control system, the human input is going to be a pulse, not a step, but the output of the system is going to still be, you'll acquire the target. And if the element that you're controlling is an accelerator, it's a double integrator, then the output of the human is going to be a bang-bang, kind of a pulse-pulse, because he's going to have to accelerate toward the target, and then as he gets close to the target, he's going to have to brake. And so to maintain the stability of the response of the circuit, the human has to adjust his gain and has to change his input based on the constraints of the properties of the system that he's controlling. And this is, Herb Simon said, a thinking human is an adaptive system. This illustrates the adaptive. To the extent he is effectively adaptive, his behavior will reflect characteristics largely of the outer environment and will reveal only a few limiting properties of his inner environment. And Rasmussen said much the same thing, but in control terms. And he said, humans do not have stable input-output characteristics that can be studied in isolation. And we cannot develop models of human-machine systems by aggregating input-output models developed in isolation. When the system is put to work, the human elements change their characteristics. They adapt to the functional characteristics of the working system, and they modify system characteristics to serve their particular needs and preferences. So to me, this is a really important insight. So let's go and look at the one way to look at this circuit in humans, and don't get too hung up on the particular words for the boxes. But from the information processing, so we get, so the information processing approach was really influenced by the cybernetic hypothesis, because at least in the US, if you wanted to be a scientist in psychology, the dominant view was behaviorism. And the idea of a mind and intentions and, thoughts and stuff, that was considered to be non-scientific. It was not tangible and stuff. And it wasn't until Norbert Wiener showed the idea of control systems, that a mechanism, we could build a system that actually pursued goals and had intention, that gave psychologists a license to bring mind into the equation. So up and then the focus was on the ecology, input, output, perceiving an action, stimulus response. But the idea of the cybernetic hypothesis allowed psychologists to begin thinking about mind and computations and things like intentions and decisions and internal mechanisms. And also the computer metaphor also helped give license to talking about a mind. I could put other boxes in here. I could put a box for the ecology, but I just kind of framed it. The perceiving and acting really are direct couplings with the world, and they kind of happen. They're what I would consider to be the embodied aspect. And then things like deciding and intention to kind of are more associated with mind and kind of mental, and sort of have an indirect coupling to the world. So cognitive, and what I want to illustrate first is, this circle. So this is another way of drawing the circle. From a controls point of view, this is exactly the same circuit. Nothing has changed. So if you look at what the output of any box is, it's identical in the two. So intending goes into acting, which goes into perceiving, which goes into deciding. And one of the difficult things about circles, so if your model is based on a causal idea, then the cause has to precede, in some sense, the effects. So you think of the time, but in the circle, what's first? And so it's arbitrary, but people in kind of building causal explanations kind of give precedence to something. And in the information processing, the ecology is kind of the stimulus on the right, and it is a stimulus that then the mind processes and then responds to. The cognitivists, they got really focused on what's happening in mind. And so for them, and often in these feedback mechanisms, the forward loop is where we think all the causal potency is. And the feedback loop is kind of the periphery, the effects of the thing. So the cognitivists, and I'll go deeper into this, but the cognitivists put the emphasis on mind. That's the top of the diagram. That's the heavy thing. And the ecology, perception, and action become a lot less important to the cognitivists. They want to look at what's in mind, and I'll say more about that. But ecological psychology, they give precedence a different way. Again, it's exactly the same circuit. Nothing has changed, but it's just how we look at it, how we draw it. But for Gibson and the ecologists, perception action was on top, and the mind was peripheral to that. They were really interested in the coupling of perception and action. And in looking at that, they said, there's all this stuff about mind and memory and stuff. Yeah, that's kind of periphery. You really got to understand the coupling. And again, I'll say a lot more about that. And then there's a fourth perspective, and that I'm particularly interested in, and I'll talk a lot more about at the end of the talk, but is pragmatism. And pragmatism shifts, whereas information processing is kind of stimulus response. Pragmatists, the early pragmatists, Dewey, Peirce, James, they looked at mind as a way of adapting to environments, that its intention, it was about fitness, it was about fitting into the world. And so they gave a lot more agency to the mind rather than a passive response to the environment. It was an active adaptation process. And so the mind's on the left as a causal, as a primary agency, as opposed to the ecology and the information processing. But the point is of this diagram is these are exactly, from control theory, these are exactly the same systems. And I think, nobody in these different camps would deny the fact that there's coupling, but they look at the coupling in really different ways. And I think those differences are interesting. So let's go back to the information processing. So the information processing view, one of the early, Miller, Glanner, and Pribram kind of introduced that, and the idea of the tote unit, and they opened up the idea of a mental, of how we can scientifically evaluate mental life with the idea of the tote unit and control systems. But notice the title of their book is Plans. And so even though they kind of take this idea of the tote unit as a license to talk about things happening in the mind, they really saw plans as kind of causal agents, and they were looking, it was still kind of a stimulus response kind of metaphor. Neisser kind of expanded on this model, introduced it to the psychological community, and his model, he didn't even show the closed loop in some of the drawings, and it was more or less a communication channel. And the emphasis of the information processing approach, while the cybernetic hypothesis gave them license to talk about the things, their mission, they defined their mission about trying to understand the transfer functions of the boxes. Okay, and different psychologists would identify with a different box. I study perception, I study action, I study memory, I study decision making. Okay, and so that the whole idea was to look at the transfer function of each box. What was the nature of the coding within the box? So what kinds of codes? Were they abstract codes? Were they spatial codes, visual codes, verbal codes? And one of the big things was, what's the capacity of these boxes? What's the limits? And so a lot of the early research was, is the bottleneck early? Is attention early or late? Where does attention happen in the system? What is the bandwidth or of these things? What are the filtering properties of these? What gets filtered at each stage, and then what gets passed to the next stage? They also, because they were interested in the internal constraints, they were very much fixated on errors. And the reason is because if you want to know what you want to know what the internal bounds are. When you think about the internal constructions, what are the boundaries? What's the limitations on memory? How much can we store? What are the kinds of mistakes they make in terms of, relative to logic, biases? But if you look at perception, at this time, almost all the perception work is about demonstrating all these illusions and the basis, the limitations. So the focus was on, looking inside the boxes, describing how information was coded within a box, and then what information got filtered out in passing through that box before it reached the next box. And there's kind of an at least implicit indication that eventually, once we understand the boxes, then we can put them together to understand the dynamics. Okay, and again, part of the early demonstration is to show that that's not likely to work, because once you connect these things in a circuit, there's going to be emergent properties that are going to be very difficult to anticipate based on knowledge of the transfer functions of the boxes. For human factors, the emphasis was on those bottlenecks. So workload was prominent. So they want to know, what was the capacity, what was the workload? Again, what is the limitation in terms of what can pass through the system? That, the mantra was basically our job as human factors people was to characterize these limitations of the humans so the engineers could compensate for these limitations or didn't overtax the human in terms of overloading them with too much work or too high rate of information input. And then also there was a large emphasis on human error. I think in Kanowitz's book on human factors, he says, if it wasn't for human error, there'd be no reason for human factors. So there was a big emphasis on human error, again, because it was seen as critical to understand what the internal constraints in these boxes were. But one of the negative side effects of that was that the implication is that the human is this weak link in the system. And so it's all about, protecting the integrity of the system against this error-prone, very limited capacity element that they had to accommodate, the engineers had to accommodate in order to make everything work. So the cognitivist view, to me, I think there are two there are lots of factors that determine kind of the shift from the classical information processing to a more cognitivist view. But I think two of them that I want to mention is first the neural nets and PDP machines, and the idea that, well, these computations are a lot more sophisticated than we thought on the basic computer metaphor and stuff. So there's a lot more dynamic happening inside brains. And so we want to get inside that mind, and we need to understand that dynamic. And then the other thing was research on expertise. And so, when you started looking at people in natural environments where they had lots of experience and lots of skill, people like Charnas and Erickson said, hey, all these limitations we see in the laboratory, they don't seem to be limiting factors. A good example was, the expertise in chess. So, the limitations, the master chess player looks at the board and he recreates the whole board. And so this idea that your experience can allow you, by chunking information, you can bypass these capacity. You don't see these capacity limitations that you see in the laboratory with highly constrained environments and puzzle solving with sophomores and little experience. And, and part of this interesting expertise, research by Klein and others started looking at people in the natural world and we began to appreciate the limitations of artificial intelligence systems. So, we still have difficulty really approximating the capacity of an expert in his domain with an artificial system. So the shift moved away from focusing only on errors, but they started to think about, well, what are people good at? And how can they be good at these things? What are the things that allow them to be so good at those things? In this view, most of the interesting activity, in their opinion, was happening inside the head. And so, it's interesting, like when Gregory talks about active perception, he's not talking about hands and moving around in the world like Gibson. He's talking about constructive processes in the brain that are actively taking, and perception, you got to have some input, so they have to deal with perception. Action gets completely ignored, and they look at perception as kind of the weak sister. You get you get unspecified, you get some cues and stuff, but they don't represent the world as it is. And in order for us to understand the world as it is, we need to be able to internally reconstruct the world, and then our actions is on this world that we reconstruct in our head, because we got a two-dimensional retina, we live in a three-dimensional world. So how can we move in a three-dimensional world based on two-dimensional retina? So we have to reconstruct that three-dimensional world in our mind. The big blind spot, in terms of human factors, the shift is from workload to situation awareness. So now it's situation awareness, but and if you look at the models of people, situation awareness in natural world, if you look at, for example, Klein's recognition prime decision making, he has loops in there, but the loops are in the head. It's loops of simulating and then testing a simulation instances. But he considers the kind of simulation, the fire ground commander kind of thinking about what his hose is going to be doing, maybe playing it out in his mind before he directs his hoses somewhere. But it doesn't include the actual directing your hoses as a test of a hypothesis or part of the decision making, as part of the thinking process. Action is not seen as part of this system. And similarly, if you look at Ensley's models, original models, all her different levels of processing are in the head. They're not in the world. They don't include closing the loop around action as something that they consider part of the problem-solving process or the cognitive dynamic. So the big gap, of course, is totally ignoring acting. And when you have a gap like that, somebody's going to jump into the gap. And that's where the Gibsons came in. And then the Gibsons said, hey, wait a minute, but how, you look at people catching baseballs, moving through the world, reaching for things and stuff. And so they put acting as a primary thing. Even though Gibson is characterized as perception, it's control of locomotion is the kind of thing, is the control of action that focused. And if you look at most of the people a lot of the people who kind of embrace an ecological point of view, a lot of them come from motor skills interest in motor skills, perceptual motor skills, and things like that, and, when you think about piloting and things like that, the motor control of airplane, concepts of optic flow and stuff become very important. So the ecologists say, hey, action's being ignored. Let's look at action and give primacy to action and that coupling of action perceiving. And, in doing that, Gibson was very controversial. And, of course they have to kind of step on the face of the people that they're opposed with. And so it's like, well, memory, why do we need memory? Why do we need mind? The information's in the world. It's not in the head. And this idea of mental models, do we really need it? And so that's really controversial, but kind of to understand, a less controversial was Eleanor Gibson's work on attunement and the development of cognitive skills. And the key difference is where most of the cognitive models thought about memory in terms of storage things. So kind of a library, a computer storage metaphor. And that they framed learning in terms of that, putting facts in the head and building facts up. But what Eleanor, when she talks about learning and perceptual learning, she talks about attunement. And attunement is really education of attention. That rather than storing knowledge in the head, what you're actually doing is learning to pick up information that's in the world and to use that in a really smart way. And what Eleanor's describing in terms of attunement, this is very much like an adaptive filter or an adaptive control system. So an adaptive control system based on, so the gain is an important aspect of stability in the system. And if the kind of signals you're trying to come in your environment changes, you need to adjust your gain. An adaptive control system monitors the behavior, the quality of the output. And if that quality starts to get unstable, they start to see oscillations and things. They use that as information, and then they'll adjust the gain, tune it up or down. They don't have to remember this. The adaptive control system doesn't have to store anything, but it's continually monitoring his performance, and it's adjusting internal constraints based on what it's learning. And this is a different kind of learning. And it's when we talk about when Gibson says no memory, what he's saying is there's a different way to understand learning other than just storing things in the head. And one way to think about learning is in terms of attunement and, refining your vision, refining how you look at the world. So to pick up the cues that are diagnostic, learning to see what is useful, and in terms of controlling action. So one of the key concepts that Gibson introduced was the idea of affordance. And when they looked at controlling action, it suggested the idea that, so classically the cognitivists, when they're, and even the information processing, when they were scoring perception, they were scoring human performance against the parameters the way the physicists look at the world. So they were looking at perception of length, and they were comparing it against rulers. And the idea is that, and when our perceptions didn't line up with those, the way the physicists understood the world, that was considered errors. But Gibson said is we don't need to know the world the way the physicists know the world. We need to control action. And so we don't need to know distance to the car in front of us, but we need to know whether we're too close or for our brakes. We need to know whether we're a safe distance. And safe distance is not one-to-one with absolute distance. Safe distance depends on how good the brakes are in my car. It depends on the action. And so what Gibson proposed, again, the key idea of affordances is our perception system is designed not to recreate the world as physicists understand it. That our perceptual system, we can do that as scientists, but as day-to-day interactions, our perceptual system the primary function is to control action. So we need to know, can I grab this with one hand or two hands? We need to see the world. We need to see the size relative to our body. We have to, the parameters that are important are not the parameters. You know, physics model of the world is designed to be observer independent. But for controlling action in the world, we need to understand the world distances relative to our body, relative to our hand size, our arm length, our height, our shoulder width, our leg length. These are the critical things for controlling action in the system. The most controversial aspect of Gibson was that not only were the primitives of perception were different, but that much of the information is out there, that you don't need a three-dimensional model, that you can look at patterns in flow fields like the expansion pattern to tell you the imminence of collision with the car in front of you. And that for much of the information for controlling action, there is at least enough information, and Neisser later would argue that there's actually more than enough. You know, there's multiple ways to look at the world, and there's multiple useful ways, so that the information, the world is actually rich in terms of the kinds of information that we need, at least the kinds of information that we need to move around in the world without running into things and to control, you know, when we're in the animal phase of our life rather than the plant phase of our lives. Now, the fourth way actually, in my mind, goes back to William James and C.S. Peirce, Dewey, and that actually predates the cybernetic hypothesis. But they're the thing that stimulated them to think about the functions of psychology, think about psychology functionally in terms of a circuit, was Darwin's theory of natural selection. So for the functionalist psychologist, early functionalist psychologist, the function of mind was to improve our ability to survive in the world. It was practical, it was utility value. And again, it was the mind gave us an agency that allowed us to adapt to a broader range of environments, and again, enhanced our capabilities of survival. So natural selection is a circular dynamic. And so when they framed behavior in terms of that dynamic, and again, you know, like Gibson, they were much interested in, it's probably most reflected in Dewey's work on education. I mean, they weren't interested in just learning as an abstract thing, but they wanted a practical education. And what are the practical education? Again, it wasn't just kind of an academic kind of learning, but what Dewey was interested in was practical education and design of schools that help people to, in their careers, in their everyday lives, and in their things. So he's very much interested in practice. One of the interesting ideas that came out of that, and by the way, the functionalists kind of fell into the background because of the success of the computer metaphor and things like that. So I didn't hear about Peirce until very late in my career. And actually, one of the first things that Peirce and the idea of abduction, I discovered in robotics. And it's really interesting is that the computer scientists, you know, when they were dealing with computers and as abstract computational things and things that sat on desks and didn't move, it was a logical thing, and that kind of supported the cognitivist information processing views of the world. But when computer scientists started building things that moved in the world, they realized, hey, you know, it's not the logic of knowing and differentiating what this robot can walk through, or what's a gap what's reachable, or how to grasp, or how to maintain balance in the world, is a lot different than this abstract logic that sits on my desk. And so they began looking at abduction. It means, and the abduction, what Peirce argued is, hey, if you look at natural rationality, it doesn't look like logic. That the way we work in the real world is essentially trial and error. And so an abductive system is this: is we generate a hypothesis. And the hypotheses are based on our experience, our prior experiences. So we get in a new situation, we generate a hypothesis about how to behave appropriately. So I'm the fire ground commander, I see the fire, I have a hypothesis about where to direct my hose. And I direct my hoses to that part, and does it do what I intended to do or not? Does it give the effect that I anticipate or not? If it doesn't, that's information that I use and I redirect my hoses. That the action is, so that abduction is you make a guess, essentially, a hypothesis. Peirce also called abduction hypothesis. We make a hypothesis, we act on that hypothesis based on our experience. If we get surprised, then we revise our hypothesis to reduce the surprise. So abduction is actually an analog to a control system. So in a control system is minimizing error, an abductive system is minimizing surprise. It's exactly the same circuit that Peirce described. And so for the pragmatists, they were very much interested in a holistic view of how mind helps us adapt to the world in a holistic world. So, and so the, intention is primary. It's the agency. It's what you want to accomplish, what you want to do in the world. And, I think this is reflected in work, for example, if you contrast Kahneman with Gigerenzer. So Kahneman was focused on the biases, and, Kahneman and Tversky were very clear, these things generally work, but most of their attention was when they didn't work. And they saw heuristics as a deviation from the ideal normative logic. But Gigerenzer looks at those same heuristics and says, hey, these actually might be really smart adaptations. And in fact, Gigerenzer has done a lot of research that shows you when you look at the constraints on information, the natural constraints in natural environments, decision-making environments, a lot of these heuristics perform incredibly well and rival and maybe even in some cases exceed what the more classical formal logic would do in those situations, given access to data and other constraints. So when we look at the politics of science, its question is who's right? And if the cognitivist is right, then Gibson has to be wrong. If Gibson's right, then the cognitivists have to be wrong, and the information processing people have to be wrong. But I think there's a possibility that everybody's right. Okay, again, the point is it's the same circuit, but these are different perspectives. And I would argue that none of these perspectives are privileged, and each of these perspectives potentially reveals something that's useful about this. And certainly these things are not as a simple circuit. And one way to think about how both can be right is when we think about multiple circuits. And this is a model based on Rasmussen's idea of skills, rule-based, and knowledge-based control. You can think about coupled circuits. And you have kind of a skill-based interaction, when you're driving the car, but you also have rules and you also have knowledge. And that is, you can have in the skill base, attunement might be a dominant. So kind of Eleanor Gibson's idea and Gibson's idea of attunement maybe have a very strong influence. But that doesn't mean we don't actually store knowledge in head and remember things and store memories and things. So both things can be right. It doesn't have to be one or the other. And in fact, it's likely that they're both going on and they're coupling and they're shaping each other. So as we learn, as we get better and we begin to tune our driving skills, we're also learning about cars and facts and things. And these things all work together. In this diagram, in the note that there's two kinds of coupling they try to illustrate. And one are the narrow arrows. And those are kind of the passing of information. And those are kind of the classic views. And so, the connection between the knowledge-based control system and the skill-based control system might be kind of in the form of internal speech even, so when you're playing tennis and your tennis game is going to pot and you start coaching yourself internally and telling yourself, oh, get your racket back, and telling yourself, that's the kind of connection that the thin arrows are representing. And by the way, one of the reasons it's a very bad thing to do that is because that circuit, the knowledge-based circuit, is really slow. And that's going to actually make performance unstable at the gains you have to perform to do the tasks. You're much better if you blank that out, as the Zen says, the no-mind approach, and let your skill-based control system do what it knows how to do. The thick arrows represent a different kind of, a less explicit kind, but a kind of an implicit coupling, where the outer layers set constraints, boundary conditions on, so, how we think about the world. Those are constraints. For example, our knowledge of the world might influence the kind of possibilities that we consider at a mutual skill-based control level. And so, so for example, the Fosbury flop, for a long time, nobody considered the fact that if you went over a bar backwards, you might be, that's a kind of a constraint on the search process in the skill-based control, that when that's eliminated, now you have a whole range of possibilities. So there's multiple interactions between these things. When you frame the question about dynamics, though, you don't have to tie it to brains. Now you can actually talk about team cognition, organizational cognition, because it's not about the embodiment, it's about the dynamic. And this is very much the same model, but instead of identifying the layers with skill and rule-based and knowledge-based, Thompson, when he talked about organizations and actions, talked about within organizations how they coordinate. And they can coordinate by standardization. And so this is kind of a cultural constraint. These are standard operation procedures. These are things that are based on long-term experiences of an organization. But then you can have planning within organizations and scheduling things to work. But then you also have real-time mutual adaptation. And so you can have these layers of constraints. And so these two systems are analogs. One's operating in organizations, one's operating at the level of an individual. So kind of to sum up, I'm getting near the end here. When we look around these circles, I think it's really important to take a both and perspective. And again, this is a very ecological perspective in the sense is, no matter where you stand, you only see one side of a cube or one aspect of a cube. To really experience the three-dimensionality of a cube, you've got to move around it. And its motion becomes very important. But as scientists, I think it's very important that we can move between these perspectives. That we need to take a both and each perspective, I think, offers different insights in the other perspectives. And they're coupled. I think we need to be able to move a good scientist, or not necessarily an individual, but a science has to be able to move around this circuit fluidly. And so that, as you change your ideas of the holistic dynamic, that's going to change the kinds of questions you ask about the transfer functions and how the boxes behave. And I think there is really interesting dynamics that happen in the mind, but there's also really interesting dynamics that happen in the world, in that perception action loop. And the other kind of either or issue that clouds things is a holistic view versus a reductionistic view, or research in the laboratory versus naturalistic observation of the world, more holistic. The fact is, if we want to do controlled research and experimental research, we have to have a reductionist mindset. But we have to do our reductions. Our reductions have to be informed by an understanding of the world that we're trying to represent in the laboratory. And so and almost even when we go into the natural world, we can't look at everything at once. So we as scientists have the same limited capacities as all the individuals. So we have to be reductionist in our operations, but we shouldn't be reductionist in our theories and our contexts. And so again, I think it's very important to be able to move around this loop in terms of the muddling that we need to do as scientists. So in conclusion, to read more about it, these are a couple books that you might be interested in. The first one is a really interesting read, and this is about the dark hero of the information age. This actually tells you about the Macy Conferences and those early interactions between Norbert Wiener and McCulloch and Pitts. And it's actually a soap opera. I mean, it really talks about the social interactions and how the social interactions and personalities and disagreements between these people had a huge influence in the direction our science took. And one of the really interesting characters is Walter Pitts. And it's worth just learning about his background, his history. Really interesting character. The Control Theory for Humans is a book that Rich and I wrote. That's if you really want to get into the mathematics of how these work. And most of the mathematics in this book are linear, and they're not going to extrapolate very far into the complex dynamics of when you think about multiple coupling loops. But for me, this was kind of like the push-ups, the drills that helped me develop the intuitions that I think were very useful when I look at the world and think about. So it's the analytics, being able to play with the analytics. I kept surprising myself, when you put the equation, you worked out the equations, and when you actually saw how they worked, and you realize you can't trace a signal around the loop, that the differential equation modeling this, it's happening at all parts of the equation at once. It's not a sequential relationships in that equation. It's a constraint over the entire process. Meaning Processing Approach to Cognition is a book that we recently published. We had published it self-published it earlier with the title What Matters. But this really kind of talks about these ideas and how I think they should shape up the ontological and epistemological basis for our cognitive science. The last two books, Rob Gray, The Move is a recent book on coaching and stuff, but I always look at the action people I think are ahead of everybody else, in my opinion. Because if you're interested in skill, you can't ignore perception. If you focus on perception exclusively, you can use byte boards and you can rule out action completely. You can totally eliminate action, but you can't study motor control and ignore perception. And so the motor theorists are the people who I think really kind of see the big picture in a way that's unique and valuable. And the last book, my advisor, Rich Jagosinski, just pointed me to that. And I haven't read that, but Rosenblum, does a lot with dynamic systems. And I just read the blurb for this book, and a lot of the themes in this talk is resonating in his introduction to this book. So these are some things that you might want to look at if you're interested in these things. So if there's time, I don't know how we do questions on here, but I'm gonna.
Thank you, John. So we have some time for question, not a lot. I will first look if there are any hands. No hands. So please let me know if you have any questions. Because otherwise I will start. Oh, go ahead,
Yeah,
Scott.
so this is not so much a question, John, but a acknowledgement of of what you're talking about, and it's in something that my colleague in California and I are involved with right now, and that is, and I know this is very constrained in terms of what we're looking at, but we're looking at eye movements, and one of the things that we just we built a model, and we're trying to get grant funding, but we basically for forever people have thought of the pursuit eye movement system and the saccadic eye movement system as separate, and that just goes back to when they sort of decided what they thought that these two systems were for. And then interesting things that are coming up in like physiology, where you have overlap of neural systems involved in both. And one of the things that we just did is we had this is work where we're trying to understand coordination of the two eyes movements, and we actually created a model where what we figured out from the data is that we needed to have both the pursuit system and the saccadic system contributing to all eye movements. And when we put them together, suddenly our model without, I mean, it's very simple, not complex at all. We didn't, put much in it, but suddenly we were able to generate, it predicted these behaviors that people have sort of marveled at. In fact, one of them is the paper was published and the title was "The Remarkable Saccade," where you have a target that is aligned with one eye and it's moving towards, and it moves towards the observer, and the eye that is lined up with shouldn't move at all because it's lined up with the eye, and yet that eye makes this saccade when the other eye does, even though it shouldn't move. And people marvel at that and like, wow, how does that work? Because the saccadic system is doing this, that. Well, we put these together and it just did it. So just as you said, when you put integrators with together and you have gain units and in this one there's actually multiple places, suddenly we just get behaviors that people observed and it can account for them. They're not, so one of the experiments in the grant we proposed was I titled it, "Is the Remarkable Saccade Not So Remarkable?"
Yep.
But rather a consequence of the way this is put together.
So I'm smiling because I probably didn't express it well, but I think I suggested this to you about 10 years ago, but and actually suggested some models. But you remind me of something that I actually wanted to say to talk about. So one of the things when we look at the dynamics of these systems, so this idea of thinking fast and slow, and in his book Kahneman acknowledges this idea of two mechanisms is a metaphor he uses, and not to take it too seriously, but then he pushes that metaphor about as far as you can, and I think it's the wrong metaphor. So if you look at that multi-loop system, the skill-based and rule-based and knowledge-based, think about it instead of not two mechanisms, but more in terms of phase transitions in dynamical systems. So, just as ice, has different qualities. So the qualitative distinctions that Kahneman describes are real. Everybody knows that, the difference between automatic and controlled deliberate processing. We've all experienced it. The phenomenon is real, but it's not two mechanisms. I suggest not two mechanisms. It's different. It's like the phase transitions in water from ice to water. As you turn up the temperature, it goes from ice to water and to steam. They're very different qualitative. I think if you look at the information coupling and the level of experience, as the information couple gets richer and richer and experience, and which is a function of experience, then you go from deliberate knowledge base, what looks like that's dominated by the outer loop in that model, to skill base, which is dominated by the inner loop that has been tuned to the information over time. And so we don't think about it. Those loops are not three mechanisms. All three loops are always active, but the qualities you see on the output side may be dominated more by one of those circuits than the others, depending upon the coupling, the environment, the nature of your experience, and a lot of factors. And understanding those couplings that cause those qualitative distinctions, it's a much better metaphor for thinking about those. And you can look all around. I mean, psychologists are great at reifying things. Every time they see a qualitative distinction on the outside, they invent a new mechanism on the inside to account for it.
So John, we have a question in the chat. I don't know if you read it or you want me to read it.
I have to open
Maybe,
the chat. Go ahead.
Maybe Maria Teresa can just say it directly. Can you say it, Maria Teresa? Looks like she needs to unmute herself.
No, I just read it. So she's asking, what
Yeah.
is the role of emotion in this? And, in our book, we have a whole chapter on emotion, and I think it's very, very important. And again, classically, it's the same thing about we've treated emotions as noise, and so we talk about logic as cold logic in the computer and stuff. But I think the whole idea of embodied cognition is these emotions are actually kind of reflect tuning to the environment. And when we're happier, when we recognize things or feel our feelings, and I think some people would make the case that these feelings are tuned over generations, not just in an individual experience, but that eventually things that are very important to survival get hardwired. And emotions, you can think about emotions as a way that couples us to the meaningful aspects of the world in a very interesting way, and helps. Again, the same thing from the view of the functionalist psychologist. What are emotions for? What are they good for? And I think what they're really good for is directing our attention, letting us know when things aren't not quite right or strange. And so, just feelings of comfort and nervousness. And then, these are things that are actually, I think, useful information for shaping how we adapt to the world.
Yeah, I agree. Thank you so much.
So we are in the extended time, but I just take advantage of John being here to ask one more question. So sometimes I can recall a piece of knowledge from my mind that I know I have slower than I can just Google it. And this kind of reflects the availability of knowledge in the world now more and more than in the past. So what would be the implications of this for education? What should we teach the youngsters nowadays?
So, I think, so one of the broad implications, and this I point to the work of Hutchins and others, is the idea that we're talking about that cognition doesn't happen in the brain, it doesn't happen in the body, it happens in the coupling of the human and his environment. And so what we're really talking about is our joint cognitive systems, and Google is part of our joint cognitive system. And so, for me, so when I was trying to learn about control systems and stuff, if I wanted to vary a parameter in a differential equation and see what the function is, I'd have to do the equation, compute point by point, and draw the graphic by hand, and then change a parameter and redo it and draw that graph by hand. Now I can go to MATLAB and I can put and tweak a parameter and see in real time how it changes the input output. So I think I think that as we have better memory, better artificial memories, better artificial visualization tools and things, they make us all smarter. And I think part of education, education is going to part of a big part of education is how to use these tools skillfully. For me, this technology is not a threat, but an opportunity. And of course, it's an opportunity that can be leveraged intelligently or poorly.
Thank you. We need to stop here. Thank you, John, for coming and speaking to us. Thank you all for your participation. I will make sure to send the information about this to everyone who needs it, who was not available to join us today. And I'll see you next time. I'll see you all next time.
Thanks very much for the opportunity. Thanks, everybody, for coming.
Thanks, Jan. See ya.
Bye.
Thank you, John, and thank you, everybody. Bye.
Good to see you, Marie.